Hello? All right. Good afternoon. My name is Chunhua. People call me Charlie. I like it. Today I'm going to present the signature of the CO snowline disks using the CO data itself, and more importantly, using the chemical imaging of the other molecular species. So snowline. The snowline, conventionally, snowline is the water where water starts to freeze out in the disk. And inside of the snowline, planetesimals forming in the disk are rocky, and outside they are icy. So in our solar system, this snowline corresponds to the divide between the inner terrestrial planets and outer gas giants. Snowline have the potential to enhance planet formation efficiency by increasing the mass, surface density, and also through the stickiness of the icy grains. So it is crucial for the planet formation. Today I'm going to talk about another major snowline, which is a CO snowline, which is actually further than the water snowline because it's the colder freeze-out temperature, lower than 20 Kelvin. This kind of CO snowline actually provides similar effects of the water snowline, but also regulate the CO ratios in the planet atmosphere. So it's important to locate where the CO snowline in the disk. CO has been obtained for decades in the disk, but it is not straightforward to determine the CO snowline in the disk, even if you have enough resolution and sensitivity. Here is an example of two best studied disks around the T Tauri star, TW Hydra, and the Herbig star HD 16396. Here shows you the beautiful Keplerian rotation around the star and extended out to several hundred AU. So is this the emission edge is the snowline is? It can be because it will be too cold in the midplane, a few Kelvin. So it turns out it's quite a challenge to determine the CO snowline just because in the disk, the radial and vertical temperature gradients. The disk is heated by UV radiation and X-rays near and around the stars. Then the temperature decrease not only radially outward, but also vertically toward the midplane. So the outer disks have a layered structure. On the surface, there's PDR region. In the intermediate, there's a warm molecular region, and in the center, in the midplane, there's a freeze-out region. So in the case of the CO will freeze out in the midplane. But when on the surface, when the surface is hot enough, over 20 Kelvin, CO will be in the gas phase. So it will extend it further away to large radii. So it's quite tricky to determine the location of the CO snowline because it's hidden inside of the big envelope of CO emission. Not only that, the stronger CO lines are awfully thick. So different transitions showing actually probing different kind of layers of temperature structure, where much weaker isotopologue emission can probe the whole bulk of the CO. So this is the first attempt to trying to understand the CO distribution using the suite of CO emissions used at SMA on the HD 16396. Multi-transition, multi-isotopologue with higher spatial resolution, spectral resolution, and also high spectral resolution. But not just the spectral, I would say. I emphasize we are getting images. So the channel maps is actually the projected emission at the line of sight at each velocity beam. As shown as mentioned, just because of the kinematic, the Keplerian kinematic feature, we actually can use the image to constrain much better size constraint than the beam allowed. This is called a super resolution. Let me describe our empirical approach of spectral line modeling. We start with the SED fitting, giving all this information of the temperature and temperature and density. And we fit the vertical boundaries. Since we have a layer structure in the molecular layer, we constrain these boundaries, also constrain the radial distribution of the column density. It's a power law column density. Adding together, putting into the Monte Carlo calculation, radial transfer calculation, and resample the visibility, compare with the data, and calculate the chi-square. We determine those properties. So you say, why we don't go through this approach? Because in this way, we can divide the task into several steps. At the minimum, the fitting parameters in each step. Minimize the parameter in each step. Here's an example for the CO. So we set up these models by matching SED fitting and also resolve the minimum continuum emission. This will constrain the stellar accretion parameters. Also this structure like density stuff. Then we can constrain the vertical temperature structure by fitting the multiple CO transitions because they are optic fit. And also, because it's bright, we can determine the geometric kinematic properties like inclination, like velocity, system velocity. Then we can determine the CO distribution. Once we have all this, we can determine the CO distribution by fitting these isotopological emissions. So first, let's briefly the stage one. We have this accretion disk model based on the D'Alesso's physical model. Then we can determine the exponential tapering edges using the resolved continuum. There's one problem. Just that for SED fitting, we don't know much about the vertical temperature is quite uncertain. So we probably can constrain the surface and the midplane, but how the temperature rise in the vertically to the surface is really unknown. And Sean mentioned that the grain is known to settle, to grow. The growth of the grain is actually affect the temperature, the vertical temperature very much. We explore the settled disk with the two populations, small grains in the disk atmosphere, big grains near the disk midplane. So the height transition is actually regulate the vertical temperature profile. See, the numbers is actually in the unit of the gas scale height. So small number, see, you can see the different Z big values is giving you different kind of vertical temperature profile. Actually, this can be picked up by the optic thick CO transitions because especially the CO625 because it's higher excitation conditions, 120 K, compared to the 2-to-1, 3-to-2. So different models. CO625 really give a discriminant among different models, even though different ZBig model can fit the data equally well, but there's this model fits CO625 best. So once we constrain the CO models, we can determine the CO distribution, determine these vertical boundaries, and this especially the midplane boundary, which is around 90 Kelvin. That's where we think is CO phase out. And also we can no radial abundance of abundance of CO. The CO abundance ratio is cosmic in its cosmic values. So this is just showing you it's really a very good fit. CO 2-to-1. The first line is the data model and the residual 3-to-2, 6-to-5, 13 CO 2-1, C18O, C17O. So I'm trying to say. So this is the temperature and the number density contours of the disk. And the shaded area is where we determine the CO distribution. So you can see that this is how we determine the CO snow line, is that outside of 160 AU, you don't see that much CO emission in the midplane. So you can see that you need a very detailed model determine the CO distribution. Is there an easy way? If you look at the column density distribution, you can see the CO drops like more than 2 orders of magnitude here. They're bound to have some chemical effect. If we look at the chemical effect of CO phase out N2H plus, the formation of N2H plus is mainly from N2 and H3 plus. But most of H3 plus will transfer a proton to CO when CO is around. Even N2H plus is formed. N2H plus will also transfer a proton to CO. So you can see that the fate of the N2H plus is doomed when CO is around. On the formaldehyde, the formaldehyde chemistry is a little bit complicated because they can form either from the gas from the surface, grain surface. But on the grain surface, it's directly related to CO freeze out because you can have the hydrogen, CO ice hydrogenation with you just keep adding a hydrogen onto CO on this grain. So if this is the main mechanism of forming H2CO in the disk, and it can photo evaporate out, it should correlate with an N2H plus, and it will pick exterior to the CO snowline. We are starting to see the signature of it. We carry out a big survey of the molecular line survey called DISCs, which survey 10 lines in disk around stars, spectral type between M to A stars. One interesting result is that we see there's correlation between N2H plus and H2CO. This is the integrated intensity, with correction with the distance and also the mass of the star. See, the flux correlation is statistically significant at 95% level. And another hint of CO ice regular chemistry is the H2CO. We detect multiple H2CO transitions. We can determine the excitation temperature is around 20 Kelvin or lower. So this is another way to say. So chemical effect of CO snow line, you see that N2H plus and H2CO correlated and then supposed to be outside of the CO snow line. But I would say the ultimate test is that whether we can see a ring structure. So we started to see this kind of thing because we imaged the N2H plus H2CO in TW hydro H2CO. We see the offset. Not just the offset, you can see that the channel maps also is consistent with the ring structure. So on the ARMA Cycle 1 proposal call, we submitted a proposal to try to resolve this. So this is N2H plus filter 2 in SMA. See, there's a big beam showing here. So if you assume N2H plus only exists at a temperature lower than 20 K, you should be able to see a ring size, N2H 3 to 2. So this is a simulation for cycle 1. But fortunately, we don't have to wait that long. We put the N2H plus another line, 4 to 3, in cycle 0 in one cycle 0 project, which has been observed on last November. This is real. So this is indeed telling us something about, this is the ring structure, is telling us important information about CO snow line. Here's another view of it, compare with the continuum, compare with CO theta 2 image and N2H plus 4 to 3. So the clear morphology difference can be explained by CO snow line, the presence of a CO snow line in the inner edge of the N2H plus ring. So in order to quantify that, we need to determine how large is the ring size, and also make sure the inner ring, the temperature is around, find out the midplane temperature, whether it is consistent with the CO freeze-out temperature. So we have this model, and we just quantify this ring structure. We can determine the inner radius ring is around 30 AU. That's just about the Neptune scale. So data model, you can see the residual. And if you look at the midplane temperature around 30 AU, you can determine the midplane temperature is around 16 to 17 Kelvin. That's exactly what we are looking for, is a CO freeze out. So one thing I would emphasize is that this is N2H plus simulation, and we assume 13 CO also 13 CO also freeze out at around 17 Kelvin. You can see it also fit the C18O and 13 CO data very well. This is the power of this kind of modeling. You can see that N2H plus modeling, 13 CO modeling, The significance of the chemical imaging is that not only you can determine the CO snow line, but also you can see, you have to have significant CO freeze out in order to see this kind of ring structure. So this is the detection limits of the N2H plus. See how many magnitude you have to raise in order to see the ring structure. To summarize the whole thing, locating the CO snow line, you have two ways. Using CO itself is really time-consuming detailed modeling, but chemical imaging is really a powerful tool to determine this CO snow line in large samples of the disk. Future structural snow lines, you can look for this signature of the chemical snow line. You can determine those snow line in different kind of snow line in the disk and help you to constrain the structure of the disk. So I can help to just show you the channel maps. This is the data of N2H plus. This is the model, and this is residual of that. Thank you.
Okay, we have time for a few questions. So I'll ask the first question. Can you talk about some of the pros and cons of tracing the snow line in these different molecular tracers?
I think the thing is that you should understand chemistry. That's the tricky part. Is that for example, the N2H plus chemistry is quite well established. You can use that. For example, for the formaldehyde, you have different kind of formation mechanism. It's kind of tricky to see whether it can be useful or not. But we see this correlation, maybe it's useful. So we're going to look for the formaldehyde line to see how it looks.
We have a question here.
I have a question about the difference in temperature in this, disk vertical temperature profiles between the midplane and the surface. Have they been calculated from the self-consistent radiation transfer modeling, or you just assume them to be some free parameters? The difference seems to be quite large. It's 120 Kelvin at the surface and only 17 or so at the midplane. So how did you get those?
Well, that's indeed, that's in the Paola's model, which has real self-consistent radiation transfer code to calculate dust temperature based on the SAD. Yes.